Introduction to chain rule. Let's think about the following situation where y is equals to x squared plus 1 squared, and you're trying to figure out what y prime is. Let me show you what the chain rule is. The chain rule looks at a function and it's applicable when the function is a nested function. So if you look at here, this highlighted part, this is what we call nested. It's a nested function, and another name people often use is inner function or inside function. So if you have a function inside a function, see, the outside function is what? Squared. That's the outside function, right? And the inside function is x squared plus 1. Okay, so what is the chain rule? Chain rule is the rule that you have to follow in order to differentiate nested functions. When you have a function inside a function, you have to use the chain rule. Now, what is the chain rule? What's the formula for the chain rule? Well, I'll write down the formula for you, but I'm not so sure if it's readily usable. You'll need to get some explanation about how to use it. So here is the chain rule. It says you differentiate the outside, leave the inside, and you bring this out, and then you differentiate the inside. Okay, so in our case, the way we think about this is we think about the outside function. Let's call the outside function as f. So what is the outside function? This is the outside function, right? And into this function, we're plugging in g of x, which is x squared plus 1. So that's the setup for this one. So if you make f as this, well, it's a little weird to have nothing in there, but basically what I mean is that whenever you plug in anything, so for example, if you have x squared plus 1 here, then you should put the same x squared plus 1 there. That's what the outside function is. But let's just put a placeholder here. We'll just put it as x here. And if you have this, then of course f of g of x would be f, well, g of x is x squared plus 1. So since f is whatever you plug in here, it's that thing squared, you're going to end up with x squared plus 1 squared, which is exactly the function that we were given. Right? So if you're convinced that this function looks like this, then we're able to allow this formula to do the work, because now what is a f prime of x? That's derivative of x squared, which is 2x, right? So this formula says it's 2 times x, but instead of x you have g of x, so we should be plugging in g of x. It's really 2 times x, but in place of x you have g of x. And then g prime of x is the derivative of this, which is 2x, right? So that's 2x. And since g of x is x squared plus 1, I mean, if you want to simplify, maybe for this, if you expand, that's simpler, right? So that's 2 times 2, which is 4x. 4x times x squared is 4x cubed. 2x times 2 times 1, that's 4x. So that's the answer. So this is what we got. We had x squared plus 1 squared prime, that's equal to 2 times x squared plus 1 times 2x. Right now, I was just demonstrating how the formula is used. We will make it a lot simpler. That was way too crazy. But don't worry about it because we're going to make it a lot simpler. But what I want you to show you before I show you how to use that formula is that indeed this gives you the correct answer. This is one of those rare cases where you can rewrite it. You can rewrite this thing and you can just differentiate as it is. So for example, what is x squared plus 1 squared? This is x squared plus 1 times x squared plus 1. X squared times x squared is x to the 4th. X squared times 1. 1 times x squared. 1 times 1. Okay, so we have x to the 4th, 2x squared plus 1. Okay, so you can simplify this just by expanding it, and that's a lot easier to differentiate because it's just a plain differentiation with power of x to the 4th. 4 comes down, you subtract 1 off of 4, that's x, 4x cubed, plus 2 comes down, so it's 4x, and that's indeed what it is, right? I wrote this down, but we actually had simplified it and wrote it as 4x cubed plus 4x, right? So this is 4x cubed plus 4x according to our chain rule, and we verify that it's true because it's like one of these rare cases where you can make it as non-nested. Just like the only way you can avoid having to use the product rule is if you can write it as not a product. Same thing happens here. If you happen to be able to write down the function not as a nested function but as just a regular polynomial, then you can just use the rules of the polynomial differentiation just to get this, right? Whereas if you leave it like this and if you wanted to differentiate it, then you would be forced to use the chain rule. Now, with just this example, you might think, well, I'm never going to use it. I'll just stick to this. Well, that may not be so feasible because suppose you have x to the x squared plus 1 to the 10th power and you were to differentiate this. Well, trying to expand this to the 10th power will require pages and pages of work, so it's not very feasible. But if you use the chain rule, it works like this. The 10 so you think about this as like a big X. So you're thinking of like x to the 10th power, and that's actually your outside function. So you're thinking of x squared plus 1 as a big X, and then x to the 10th differentiates to 10 times x to the 9th power, right? You think about this as 10 times x to the 9th power. But what is your big X? What you're calling as your big X is really x squared plus 1, right? And then this, what we call the inside function, the inside function must be copied over to outside, and that one has to be differentiated outside, okay? So you have 10 times x squared plus 1 to the 9th power, and the derivative is 2x. And this is achieved through chain rule, whereas if you were to actually expand this, it'd be like pages and pages of calculation, and then you differentiate, it'll be hard to get this, okay? So chain rule definitely is the only option in many cases, and sometimes there's no other viable way, because you know, for example, e to the x squared, well, so what's the chain rule again? It's a way to think about some parts of the function as a big X. So think about this. Think about this as a big X. So what do you see? E to the x, right? What's the derivative of e to the x? That's e to the x. But what is that e to the x? X is what we're calling this x squared. So it's really x squared here. But whatever you call it as big X, that's the inside function. That has to be copied outside. And it's a multiplication to the previous one. It has to be a multiplication. And you have to differentiate that copy. the copy is differentiated, which is 2x, so you end up with 2x times e to the x squared. Now in this case, there's no way around having a nested function. This is a nested function, and there's no other way to write this as a non-nested function. So in that case, this chain rule will be the only way to access the derivative. Okay, so I was trying to explain why we would need the chain rule, and along the way I kind of explained to you how to actually apply the chain rule. So let's review the chain rule again. You have f of g of x, and when you have to differentiate something like this, you take a portion of it and call that as like a big X, and you write down the derivative of f prime of x. You differentiate the outside, with the inside still being the same thing, the thing that you're calling as x. You bring that outside and you differentiate it outside. Okay? That's the chain rule. Now, we've seen that it gives us the correct answer in the first example, and I showed you how this actually is calculated in practice by 2 more examples. I still want to show you this. I still want to show you that there's a reason why this is true, and it's easier to see why this is true if you use the Leibniz notation. So think about it like this. Let's say we want to differentiate f of g of x. Well, what chain rule really is, it's a differentiation by substitution. Just like how we solve some limit problems by substitution, we can set u as g of x, and then try to rewrite this as f of the variable u, and we differentiate. Now this is a terrible notation because this is very ambiguous, because see, when we have this prime, this is really saying how fast is f compose g, that's another name for this composition, right? How fast is this changing with respect to x? That's the question. But here, so this derivative is really derivative with respect to x. But if you write like this, because the variable is now u, many people will think that, oh, this prime must be d du. But no, we're originally asking for rate of change of this composition function, whereas with respect to the change in x. Okay? So that's why we would like to use a Leibniz notation. Leibniz notation is very good because it explicitly says with respect to what you're trying to differentiate. So here's what we want to do. We have the function f of x. It's really dependent on this intermediate function u. U is the g of x, and then u, because it's g of x, it's a function of x. So there's this dependence. If you change the value of x, that's going to change the value of u, and if the value of u changes, that's going to change the value of f. So such diagram is called dependence diagram. F depends on u, u depends on x. Okay. Now, in such a case, you can ask the following question: how fast is f changing when you change x? This is the rate of change of f with respect to x, and that's the Leibniz notation for derivatives, right? That's another way to write down f prime of x. Well, Leibniz says that's same thing as df du times du dx. And that immediately makes sense, because what is this? That's like the limit of change of f over change of u, right? That's what this is. Okay? And this is the limit of change of u over change of x. If you recall how we defined the derivatives, it was this rate of change. It was the average rate of change over some interval, and then you shrunk the interval down to a very, very small thing, right? And in that limit, that's what we called the derivative, and this has the meaning of the slope of the tangent line, or it also has the meaning of the instantaneous rate of change, right? So here, it's like this entire thing is the limit of this, and because delta u cancels, it does seem to make sense that this quantity should be same thing as that, okay? If you think about these as like very, very tiny amounts, and still positive, they cancel, and now you get this, okay? So that is the Leibniz version of the chain rule, and that's exactly what this is, because see, once you write down this as f of u, if you write down the composition as f of u, then change of f over change of u is like differentiating f as a function of u. It's like in here, you're really trying to think about the inside function as u, right? So f prime of u is df du, and then this is f prime of u, that's what you have, and du dx, because u is g of x, that's g prime of x. Because u is g of x and you're differentiating that by x, that will give you g prime of x. And finally, this is f prime of g of x times g prime of x, and as you can see, that's exactly this chain rule. So in Leibniz notation, the chain rule is very easy to see. You're almost convinced by it. Of course, there's the mathematical proof why it has to be this, and that one I'm not going to show you. Just if you're really curious to know, you should look at the textbook and follow the proof. But that is the intuitive reasoning behind why such chain rule works.